Hello to all. I want to welcome all of you to this webinar where we will explore some important fundamental truths about nature and what's been developed by Western science. These truths help us understand what biodiversity is all about. These truths tell us why biodiversity is so important, and these truths provide clues for effective conservation. First, I want to thank Bib Perriman for inviting me. What a dynamic person she is. The PBS video entitled Eden's Lost and Found that portrays her work is awesome and inspiring. I've shared this video with some of my fellow teachers and researchers as an example of how environmental education should be. The video brought tears of excitement and joy to two of my colleagues. Deb, we are all deeply grateful for what you're doing. Well, my name is Bill Graham. I'm a biologist who lives and works in Guaymas, Sonora, Mexico. For a number of years, I was associate professor in the Graduate School of Marine Sciences at ITESM, Mexico's largest private university. For the past 8 years, I have focused on connections in nature, where I have communicated my work through weekly blog postings, through nature photography, and through books that I have written. I am currently one of a number of scientists on a conservation team that is working to protect an important estuary that is connected to the Sea of Cortez. I also mentor youth as we build local programs in environmental education. I would love it if you were to dialogue with me through my blog site or directly by email. In this webinar, I will provide you with a deep look at how and why everything in nature is interconnected. I hope to instill in you a connectivity consciousness so that you will be equipped to become a steward of nature who conserves vital connections in nature. Today we will discuss the actual structure and functioning of ecosystems. We will learn that biodiversity is a healthy state of being for all ecosystems because biodiverse systems are resilient systems. We will closely examine 3 strategies that biodiverse ecosystems employ to achieve their resilience. With all of this, we will be ready to discuss ecosystem conservation. Armed with your new knowledge, I will suggest a conservation strategy that will serve to maintain the biodiversity that nature has created. But first, I want to tell you a true story. In 1924, the last wild wolves, predators of deer and elk in Yellowstone National Park, were deliberately killed by the U.S. federal government because mankind had decided that the wolf was a dangerous predator who created economic disaster for ranchers. In carrying out this program of predator eradication, important food chains were broken. The course of running streams and the quality of waterways was hampered or destroyed as the now overpopulated deer and elk ate the streamside aspen, cottonwood, and willow saplings. The result was major changes in local ecosystems. The face of biodiversity for Yellowstone National Park was altered. Our great predators, the wolf, the cougar, the bear, and others teach us about the vital importance of connections in nature. They are top predators because the power of their connecting presence is an evolutionary driver of the diversity of life. Chains of life flourish with the force of predation. In the 1990s, the previously banned wolf was reintroduced to Yellowstone National Park. The eating of elk and deer by the wolf was resumed, resulting in a reduced population of grazing wildlife and a new ecosystem diversity that has resulted in a healthier biological equilibrium. Those scientists and naturalists who facilitated this new equilibrium are stewards of nature who understand the importance of biodiversity and the energetics of this ecosystem. What makes the wolf story particularly exciting is man's role in the 90s. The conservation strategy became one of defining the broken connection, reintroduction, and then protecting the gray wolf. Man did not manage nature. Instead, nature achieved a new biodiversity and resilience all by itself. So what is biodiversity? It's a very common word with a general meaning. Biodiversity, through its variety, variability, and interconnectivity of organisms, is a manifestation of nature's strategy for maintaining stability while coping with change. We will be using the word resilience to describe stability when an ecosystem achieves a state of biodiversity. Resilience within ecosystems is the capacity of a system to absorb all disturbance and to reorganize while external environmental changes take place. Change is a normal part of nature. Evolution is change. Resilience doesn't resist or prevent change. It works to bring all parts of an ecosystem into harmony as changes do take place. Resilience is the adaptation mechanism inside of a healthy, biodiverse ecosystem. We'll be using words like complex networks, feedback, and self-organization to describe the three strategies that biodiverse systems use to achieve resilience. As we will see, biodiversity is connectivity in action. Without connectivity, life wouldn't happen. And we will learn a conservation strategy of protecting connectivity in an ecosystem protects the system's ability to transport energy and to adapt to changes using its resilience strategies. So let's dig deeper by asking ourselves, how do ecosystems operate? What strategies do ecosystems use to achieve the state of biodiversity and resilience? Well, we must first ask, what do we mean by a system? A system is a group of related parts that move or work together. An ecosystem is a system. It is a community of thriving and living organisms acting in conjunction with the non-living components of their environment to operate as a system. These biotic and abiotic components are linked together through nutrient cycles and energy flows. Ecosystems operate according to 6 organizing principles. These organizing principles contain the strategies by which life exists on this earth. These principles describe biodiversity. We will briefly examine some of these principles as we explored biodiversity. There is extensive information on all 6 organizing principles available for your review in my blog site or in my books. Resilience within biodiversity comes from the application of nature's 6 organizing principles. Resilience is a measure of an ecosystem's ability to survive, persist, and adapt within a variable environment. Ecosystems utilize at least 3 strategies to achieve resilience. We will examine each of these 3 strategies closely as we proceed today. Let's start by explaining and exploring connectivity. John Muir once said, "When we try to pick out anything by itself, we find it hitched to everything else in the universe." From the most minuscule atomic particle to the grandest galaxies, the past, the present, and the future of every animate and inanimate being in our universe is defined by how it is linked to everything else. All of nature, living and non-living, are receivers, storehouses, users, and transformers of energy. Energy is the lifeblood which drives our universe. In the course of its journey through nature's interconnected networks, energy changes into different useful forms, whether it be the flow of solar energy to Earth, the storage of energy in our plants, the metabolism of individual species, or the functioning of food webs. The primary goal of all conservation work is to protect these energy conduits, because ecosystems at all levels are useful to nature only when they are able to hold and pass energy to and from components within the system and to other surrounding systems. Energy needs to flow for nature to function. There are smaller flow patterns inside larger flow patterns. Electrons and protons beget atoms. Atoms beget molecules. Molecules join to form our body organs, mountains, and oceans. It is this connectivity that defines biodiversity. Developing a connectivity consciousness by stewards of nature, such as yourselves, is crucial to the conservation of our environment. This consciousness starts by becoming informed, which is what we're doing today. It's useful for us to take a look at the actual structure of nature's energy transportation systems, because the structure of these networks are one of at least 3 ways that ecosystems become resilient to outside environmental influences. Let's take a look. Scientists continue to work on describing nature's energy transportation and transformation networks. One such network is similar to airline route maps, which you may be familiar with. Towns and cities are represented by dots, which are called nodes. Lines, which we call links, represent the actual traffic flow between nodes. There are relatively few highly clustered hub cities like Chicago or Dallas, where flights connect with many small towns. But there are many airports whose airline routes are connected to only one or very few major cities. The major cities with many connections to smaller communities are special nodes that we call hubs. Hubs contribute heavily to the overall connectivity of the network. Small community airports contribute very little to the network's connectivity. If a snowstorm hits the region of a small airport like Ames, Iowa, there would be little or no effect on air travel throughout the route network in the United States. But if Chicago or Dallas experiences severe weather, the entire airline travel network would be adversely affected. This kind of network architecture has resilience because there are far fewer hubs than there are small community airports. Because there are few hubs, the chances of a hub being hit by bad weather is far less than weather affecting a small community airport. Nature's energy transportation networks are similar to airline route maps. The nodes in this food chain map represent species in the Southern Ocean ecosystem. The lines represent the flow of food energy. There are many nodes with few connections and a few nodes with many connections, which we call hubs. The world of science calls this model a complex network because, by definition, it contains both order and chaos, which I will describe shortly. In this diagram, that you can see that krill are a hub species because many creatures feed on krill directly or indirectly. If we were to kill off all the krill, the ecosystem might collapse. This complex network architecture contained within much of the energy transportation and transformation networks in nature. Our body's circulatory system, our rivers, and plant leaves are all examples of complex energy transportation networks. It is with this special complex energy network architecture that we encounter our first experience with resilience in biodiverse ecosystems. A key feature of the complex network that we've just described is that it can be very robust, very resistant to destruction. As I've said, if nodes with only a few connections are destroyed, the energy network will survive. If a hub is destroyed, the system might fail. But the chance of a hub getting destroyed is much lower. The schematic complex network diagram shown in this image portrays a network of species in an ecosystem with a single water source in the center. The living habitat of each species is denoted by a square shape from where a species regularly visits a number of unique locations for food. Since there are numerous links to food sources, the destruction of any one food source will probably not affect either the species or the viability of the network. That's resilience. But since this is a desert climate, there is only one water source available for all the species. If that water source were to be compromised or disappear, the entire ecosystem would collapse. Well, perhaps you've visited nature preserves where signs are posted that prohibit camping near a wildlife water source. This sign is a very strong indication that the naturalists in charge of the preserve implicitly understand the vulnerability of the ecosystem's network, even though they may have never studied network theory. Here we see a wildlife waterhole in the Chiricahua Mountains in southeastern Arizona. It was constructed by the Arizona Game and Fish Department. The local area had been leased to ranchers for cattle grazing. A small stream flowed through the area. This stream was used both by wildlife and cattle, but the cattle eventually destroyed the watering site. The wildlife had no way to get water. The Arizona Game and Fish Department prohibited any further grazing in the immediate area. A strong barbed wire fence was constructed around the old waterhole. This fence was designed to keep cattle out but permit wildlife to pass through or jump over the fence. The newly constructed waterhole is a trap for runoff water from the stream. In building this water trap, the Arizona Game and Fish Department recreated the hub in an ecological network that served many wildlife. These folks saw the water source as a hub that needed protection. They understand that the resilience of this biodiverse ecosystem depends on the survival of the waterhole. Good going, folks. When trying to comprehend nature's systems and our role as stewards of nature, there is a distinct relationship between knowledge about the architecture of nature's ecological networks and the successful conservation of our environment. Like these people have done, you being able to understand, identify, and preserve hubs within an ecosystem's energy transportation network is a key conservation strategy that results in that state of being which we call biodiversity. While we've examined one of nature's strategies for achieving resilience, the architecture of our special energy flow networks, we now take a look at nature's second strategy for achieving resilience in her ecosystems. We call this strategy feedback. It is within nature's complex systems that we see feedback. The study of nature is the study of her ecosystem, such as this waterfall within the Oregon forest. Using the terminology of Western science, an ecosystem is a complex system. The terms complex systems and ecosystems are synonymous. By definition, a complex system has a large number of members capable of interacting with each other and adapting to their environment without a leader and without a blueprint. In other words, mankind need not be present to direct or oversee nature's processes. Well, at best, mankind can accurately estimate the weather 2 or 3 days from now. How about 2 weeks from now, or a month, or a year? A 2-week forecast might be a rough approximation. A month's or a year's weather forecast would be a random guess. Why is this? Our weather is a series of interconnected systems. The basic elements within a weather system are oxygen, nitrogen, and hydrogen. They come together to form air or water. Even though the hydrogen, oxygen, and nitrogen molecules are essential components in the atmosphere, you cannot predict a storm by analyzing the behavior of these molecules. Said in another way, if you are able to manipulate the characteristics of hydrogen, oxygen, or nitrogen, you would never be able to predict or manipulate the behavior of the weather system in which these molecules operate. Weather systems operate under the same organizing principles that we listed earlier. Western science calls a weather system a complex system. In listing the weather system's characteristics, we have also just described an ecosystem, the economy, the stock market, ant colonies, and many other systems. They are all complex systems with the same fundamental characteristics. Now, complex systems in nature are both ordered and chaotic. Take a look at this mountain stream. We see both ordered water flow as well as highly disorganized, chaotic flow. We can predict some things within a system like this flowing stream, but there are other things that we cannot predict. Most certainly, we cannot control nature. We cannot control nature because it is impossible to predict nature. But yet we see a stability in nature that helps her ecosystems maintain resilience even during limited changes in climate or other conditions. Ecosystems resist change and remain in a state of equilibrium all by themselves. The mechanism called biological feedback contributes to this resilient state of being that we call biodiversity. Well, a feedback loop is a mechanism by which change in some environmental variable results in either an amplification or a damping of some behavior within the ecosystem. A familiar example of feedback is the cruise control in our automobiles. After we set the control to govern a given speed of the car, the feedback mechanism increases the throttle if the car is going slower than the set speed. Likewise, the feedback mechanism backs off on the throttle if the car exceeds the selected speed. In our cruise control, the next action is defined by the state of the current condition. Our car's cruise control and our body's thermal regulation mechanism are examples of what we call linear feedback. A single event drives an expected response. But linear feedback rarely happens in nature. Far more often, a feedback mechanism responds to combinations of varying and unpredictable inputs and environmental factors that change over time. The results are nonlinear, highly unpredictable, and chaotic outputs. Think about a population of rabbits that lives in a farmer's field. The current size of the rabbit population depends on external factors such as weather, food supply, and predator activity. Each one of these controlling factors is highly variable and usually unpredictable. Consequently, the resulting population trend is highly variable and unpredictable. Feedback systems that respond to the combination of a number of different unpredictable influences result in the complexity and the unpredictability that we see in nature's ecosystems and their organisms. This is a classic scenario for nature's ecosystems. Science calls this chaos. While producing some chaos, nature's feedback systems also produce ordered resilience in ecosystems. Resilience arises from a rich structure of many feedback loops that can work in different ways to restore a system even after a large perturbation. Ecosystems with much biodiversity are resilient because they contain many complex feedback systems that serve to correct for outside perturbations. At Yellowstone National Park, when the wolf was reintroduced, nature's feedback mechanisms were hard at work restoring her ecosystems to an earlier state. So we've now discussed two forms of resilience in ecosystems. We've noted that a complex energy flow network architecture is robust. It can still operate with a random removal of a few nodes, but the failure of a hub can fragment the system, causing connectivity failure. We also discussed the robustness of ecosystems using feedback. Now, there's one more important mechanism that nature uses to keep order and maintain resilience in biodiverse ecosystems. Self-organization results from local interactions between individuals within a system's population. These interactions take place as each individual, employing its own internal feedback system, acts according to a fixed set of rules that are either learned or genetically implanted. The result is a system that achieves an organized pattern of existence by itself without any apparent leadership or outside force. We see these aggregations in animal herds, fish schools, bird flocks, and cities. The phenomena is called self-organization. Because nonlinear feedback mechanisms are employed, self-organizing systems are complex systems that behave in unexpected ways which are not predictable from the behavior of their members. A breathtaking picture of living emergence comes from the flocking behavior of starlings over Termini, Italy. There is no leader. The individual birds fly while employing ingrained rules that separate themselves from their neighbors. The appearance and behavior of the flock tells us nothing about how each individual bird is behaving. This is characteristic of a complex system. So self-organization is a form of resilience. When predators and other outside influences affect the group, the overall shape of the group may vary, but internal structure and integrity is maintained. There is a network of feedback where peers are influencing peers. Scientists call this kind of self-organization emergent behavior. You can Google the words emergent behavior on your computer and you'll receive a wealth of information and some very exciting videos, I might add. We've now taken a closer look at resilience in biodiverse ecosystems. We've described 3 resilience strategies that nature uses to preserve her ecosystems: her robust energy flow network architectures, her feedback mechanisms, and self-organization. Now, if you think about it, just for a moment, there is one strong undercurrent that should be emerging in all 3 of these resilience strategies. That common factor is connectivity. If somehow we could protect these connections without interfering with how nature does business, we would help conserve resilience within nature. But we've also learned that nature is highly complex and chaotic. Nature is not predictable by we humans. As hard as we try, we can't control nature because we cannot predict nature. Remember the weather example? So what should we do? My answer to you is that we can set the stage so that nature can make things happen all by herself. The scientist calls this passive ecology. Passive ecology means that we humans can provide nature with some restorative act, like reintroducing the wolf to Yellowstone. But then we need to sit back and let nature take her course because we cannot control her or how she uses her connections to provide resilience. We can also be very active in preventing things from happening in the first place. Here's where your connectivity consciousness kicks in. We can prevent damage to nature's connections. In many cases, like the Yellowstone wolf or the wildlife waterhole in Arizona, we can restore broken connections. When you see something that is not right, ask yourself the following questions. How are things connected? Where and what are the vital connections within the system I am studying? I'm going to offer you two simple case studies to illustrate. You've decided to walk your dog in a bird sanctuary. Ask yourself the question, how will the presence of my dog affect the nature's connections? It's a known fact that wildlife usually views dogs, either tame or energetic, as predators. It's not just the barking that might upset the communication links between wildlife. It's the actual presence of your dog, even though your pet doesn't bark. You've affected a connection in nature. You've disturbed the biodiversity, at least for a moment. This is why dogs are prohibited in most bird sanctuaries and wildlife preserves. On a grand scale, let's look at the biodiversity of our planet. The most vital energy connection all creatures on Earth depend on is the sun. What if that energy connection were compromised or completely blocked? By now, your connectivity consciousness should be kicking in with an answer. What is important is your next question. What am I doing to help maintain that connection with the sun? An obvious answer is to switch to a more eco-friendly form of transportation that doesn't emit air pollutants. By identifying the connection, understanding the connection, and thinking about how you can help maintain that connection, you are a steward of nature who's exercising connectivity consciousness. Biodiversity is a general descriptor for some deep things going on inside ecosystems. Biodiversity is nature's state of being that results in adaptability or resistance. Resilience requires connectivity to operate. We've seen the undercurrent of connectivity in three resilience strategies: energy network robustness, feedback, and self-organization. Biodiversity is connectivity. So your take-home message today is maintaining connectivity is vital to the survival of ecosystems and their biodiversity. You can be an important part of conserving connectivity in nature by developing, maintaining, and exercising a connectivity consciousness. I want to thank all of you for your attention and interest. Part of the reason I write a blog, publish books, and do webinars is because I love to dialogue with people. I urge you to email me with your comments and questions. I'm also available to talk by phone or Skype if you so desire.